lecture. Good afternoon. We will start today's lecture of Hilbert spaces. We will continue. In the last lecture, what we have seen, we will just have a look. Okay. In the last lecture, we have seen some characteristics of the inner product. I will just show you what is the characteristic we have seen. What are the characteristics? Yeah, these are the characteristics or other properties of the inner product we have seen. That is, if x is a complex number, then these four properties satisfies. First property is very similar to linearity. Only the changes with the, instead of addition, we have a subtraction symbol, right? Second property is linearity in the second variable. Actually, we will call it as conjugate linearity because the variables or rather the scalars are taken out with the conjugates. That's why the second and third property is called as the conjugate linearity in the second variable. Fourth property tells us that in an inner product, if any one of the vector is 0, then the inner product is 0, which exactly matches with the concept of multiplication and dot product we have seen. Then we have seen one example also, that L2N is an inner product space. Now in today's lecture, we will start with the Scots Inequality, right? We have seen this concept also. Hilbert space definition tells us that a linear space is said to be Hilbert space if it is a complete inner product space, and this is what a relation between norm and inner product. This relation was established just by generalizing the concept of relation between modulus and dot product. Modulus is generalized to norm and dot product is generalized to inner product. Therefore, this is what a relation between norm and inner product. In one of the theorem, we will prove that this norm is actually a norm defined on the given spaces. Now in today's lecture, our first aim is to go with a famous inequality called as Scots Inequality. I will just write what is the Scots Inequality. Okay, write Scots Inequality. First point of today's lecture, SCH, Scots Inequality. Actually, Scots Inequality will help us to derive many theorems in Hilbert spaces. This Scots Inequality was proved by a German mathematician, Hermann Scots. Hermann Scots. He was a German mathematician. Okay, I'll just tell you quickly the life tenure of his this mathematician. It was from 25 January 1843 to 30 November 1921. Okay, we will just quickly write down. Okay, all the students are requested to please come within time, because once I have started the recording, it will be difficult for me to admit, right? Therefore, I will just write the statement of the theorem. The statement tells that if x and y are any two vectors, in an inner product space, then prove that. What to prove? Modulus of an inner product xy is less than or equals to norm x into norm of y. This inequality we are using in many aspects of the theorems of the Hilbert spaces. We will just prove this. Actually, we are proving this by considering two cases. First case we will consider is y equal to 0. Second case we will consider is y not equal to 0. Now one may arise with a question, why only these two possibilities? Because we are dealing with two different vectors x and y, and why we are considering only two possibilities. Okay, I will just change the color of my pen to discuss this point. Okay, in the proof we are discussing only two cases, y equal to 0 and y not equals to 0. But as we have two different vectors x and y, actually there should be four cases. First case is x equal to 0, y equals to 0. Let the second case be x not equals to 0, y is equals to 0. Let the third case be x equal to 0, y not equals to 0, and the last case we will discuss is x not equal to 0 and y not equal to 0. X not equals to 0 and y not equals to 0. But we have seen in the characteristics that if any one of the vector is 0 means the inner product will be 0. If any one of the vector is 0, then the inner product will be 0. Okay. Therefore, if I consider the middle two cases, here either x is 0 or y is equals to 0, means the inner product xy together will give us the 0 value. Inner product xy will give us together a 0 value. Therefore, this may be concluded in one case. One variable 0, one variable is not equals to 0. Now, what's the second possibility? One possibility if both are 0. If both are 0, what is the value again? Inner product xy is equal to 0. If inner product xy is equals to 0, if I put the value here, left hand side is 0, but we know that norm is always greater or equal by 0. Therefore, there is no point to prove the first one, rather this case is obviously true. The important case remains to discuss is x not equal to 0 and y not equals to 0. Therefore, we are discussing this by considering once y vector is 0, once y not equals to 0. If I am considering y 0, then the two cases will be included, and for y not equals to 0, either x may take 0 or non-zero. In this way, the four cases we will convert simply by discussing y equal to 0 and y not equals to 0. That is, if I consider y equal to 0, then x may take any value, non-zero, 0. If I consider y not equals to 0, x may take any value, 0, non-zero. Therefore, the four cases will be covered if I discuss by taking only the values depending on y. Okay. Therefore, let us discuss the result by considering case 1. I will write case 1, y if y equal to 0. If y is equals to 0. What will happen if y is equal to 0? Okay. We will start with the inner product. Inner product x, y. I will put it in the modulus because we want to prove modulus inner product xy. Modulus inner product xy is less than or equals to norm x into norm of y. Okay. Therefore, here I will consider it in the modulus. Therefore, what is the value if y is equals to 0? This is inner product x with 0. Okay. This is inner product x with 0. Now, we will discuss this value. Inner product x with 0. Okay. Now, we will just take a conjugate writing this as inner product 0x. Okay. Now, this 0 we will write as some 0 into a vector x say or any other vector you can write. Okay. Now, linearity in first variable we will use. Therefore, we will write it as 0 into inner product xx. Okay. Let us separate these conjugate values as 0 bar into inner product xx bar. But 0 bar, as 0 is a real number, 0 bar is 0. Therefore, this is 0 into inner product xx conjugate, which finally gives us 0. Because anything, this will be my value, a scalar value. 0 into a scalar will give us 0. Therefore, inner product x with 0 is 0. Then what about an inner product? The value in the modulus itself, this is 0. This is 0. Therefore, which I can write it as equal to norm x into norm 0. Therefore, first in the inequality, instead of less or equal, we have proved equality. Therefore, the Scots inequality hold for the first case of y equal to 0. Let us discuss the second case, if y not equal to 0. As we are discussing y not equals to 0, therefore here x may take 0 value or non-zero value. To prove this result, we will start with any scalar, say lambda. For any scalar lambda in C, we have what we have. Let me consider norm of x minus lambda y. We know that norm is always a non-negative quantity. Therefore, for any norm x minus lambda y, the value will be 0. Let me consider a square also. Why we are considering a square? Because this relation we have seen in the last lecture. Norm square of x is inner product x with x. Right? Therefore, I will consider norm square of x minus lambda y, which is actually an inner product of x minus lambda y with itself. Okay, which is greater equal by 0. Now we will just use linearity in first variable and conjugate linearity in the second variable. First I will use linearity in first variable, which tells us here we will separate this term in the first variable. Therefore this is x with x minus lambda y, okay, minus scalar lambda is taken out and we remain with the vector y with x minus lambda y is non-negative. Which property we have used? Linearity in first variable. Okay. Now we will use conjugate linearity in the second variable in both the inner products simultaneously. Okay. Therefore, actually before using this, here it's a scalar 1 used, right? Therefore 1x minus lambda y. Here also one can write 1 into x minus lambda y. Therefore let me use conjugate linearity. Therefore in conjugate linearity, scalars are taken out with the conjugates. Therefore this is 1 bar inner product x with x minus lambda bar inner product x with y. Okay. Next, minus lambda as it is, we will put a bracket here. Again the scalar 1 is taken out. Therefore this is 1 bar inner product y with x minus lambda is taken with bar and inner product y with y, and everything is non-negative, is greater equal by 0. Okay, but 1 is a real number, therefore 1 bar is 1 itself, therefore there is no difference. Here it will be inner product xx itself, and this is lambda bar inner product x with y. We will multiply by minus lambda. Therefore this is minus lambda, 1 bar is 1, therefore this is inner product y with x. Negative of negative, this will be positive, and vector lambda into lambda bar inner product y with y is greater equal by 0. Okay, now again with this relation, norm square of x is inner product xx, this term will be norm square of x and this last term is norm square of y. Therefore we will just write norm square of x minus lambda bar inner product xy minus lambda inner product yx plus lambda bar norm square of y is greater equal by 0. Now in order to prove that Scots inequality, we will select the value of scalar lambda in such a way that we will get everything in the norm quantity. Therefore what we will select? Choose a vector lambda as, say, inner product xy upon norm square of y. Why I can take norm y at the denominator? Because we are discussing the case y is not equals to 0. If y is not equals to 0, norm y is also a non-zero quantity. Okay, here I will write, which implies norm y is also a non-zero quantity. Therefore let's just put the value of lambda in the above inequality. The above inequality becomes norm square of x is lambda bar we want to make. Okay, therefore what will be a value? Lambda bar, this is bar inner product xy upon norm square of y into inner product x with y minus lambda inner product xy upon norm square into inner product y with x plus, here we want to put lambda and lambda bar both. So this is inner product xy upon norm square of y and inner product xy bar upon norm square of y into norm square of y, and everything is greater equal by 0. Everything is greater equal by 0. Now what to do? Here one norm square will get cancelled. This is in the numerator, this is in the denominator. One norm square will get cancelled. We will write the terms left with us. Okay, what is this quantity? inner product xy into inner product xy bar. Is the quantities of the form z into z bar. But z into z bar is norm square, modulus square mod z square. No? Therefore here I will write inner product xy in the modulus square upon norm square y. Same repeats here. Acha, this is yx. If I write xy, it will be with the conjugate. Therefore this is inner product xy into inner product xy conjugate. Therefore again with the same mod z square. Right? This is modulus inner product xy square upon norm square. Here also the same thing will happen with the positive sign. Modulus inner product xy square upon 1 norm square y will get cancelled, will remain with y. Okay, therefore again this cancels to one another and we left with norm square x minus modulus inner product xy bracket square upon norm square y is greater or equal by 0. We will just cross multiply, we will get norm square of x into norm square of y minus modulus square inner product xy is greater or equal by 0. Norm square is shifted to the right, it will become 0. Therefore what we have obtained, norm square x into norm square y is greater or equal by modulus inner product xy bracket square. Taking square root, we will get norm x into norm y is greater or equal by modulus square inner product xy. Therefore we will just write by changing the inequality, and modulus inner product xy is less equal by norm x into norm of y. Hence this will be a proof for the Schwarz inequality. This will be a proof of Schwarz inequality. Any doubt in this inequality? If you have a doubt, you can ask me. Yes? If you have a doubt, you can ask. Up to this, Schwarz inequality. No doubt? Okay, if there is no doubt, we will go for the next point. Okay, now we have proved for any two vectors x and y, inner modulus of an inner product is less than or equals to norm x and norm x into norm y. There is one remark on this theorem, that the Schwarz inequality, in the Schwarz inequality, equality holds if x and y are linearly dependent. Okay, that is, I write in Schwarz inequality, in Schwarz inequality, comma, equality holds if and only if x and y are linearly dependent. Can anyone tell me what is the meaning of linearly dependent? Two vectors are linearly dependent. Yes? Two vectors, when we say that two vectors are linearly dependent.
The one of the vector can be written in the scalar multiple of another.
Right. If one vector is written as the scalar multiple of another. Here shall I write? That is, one of them is scalar multiple of other. Okay, we can just check. Suppose I am writing a vector y as a scalar multiple of x, that is y equal to alpha x. What is the value of this left side? Modulus inner product xy. What will be a value? This is modulus inner product. Why we are writing alpha x, right? Therefore, by using a conjugate linearity in second variable, what I can take? This scalar will taken out. Therefore, we remain with inner product xx. Right now? Then this is mod alpha bar. Okay? This is mod alpha bar into norm square of x. This will be a value. I'll call this as say 1. Okay. What is the right hand side value? Say norm x into norm y. Therefore, this is norm x into norm of alpha x. But what we know the fourth property of norm? That scalar is taken out with the modulus. Scalar is taken out with the modulus. Therefore, this is, I can write mod alpha into norm of x. Therefore, what we have obtained? Mod alpha into norm square of x. Now, what is the relation between mod alpha and mod alpha bar? Conjugate modulus value of a number and modulus value of its conjugate. What is the relation? Yes, can anyone tell me the relation? Mod alpha and mod alpha bar. Let me call this as equation number 2. Yes, what is the relation between the two? Anyone can tell me the relation? Mod z and mod z bar. Are the values equal or not?
The sign is different.
Which sign is different you are saying? Modulus we are checking, na? Sign is different in alpha and alpha bar. Suppose I am taking alpha bar as a plus ib, then alpha bar will be a minus ib, right na?
Yes.
But what about their modulus? Modulus value?
Equal.
Equal, na? Because mod alpha will be under root a square plus b square. And what about mod alpha bar? Will be same. Under root a square plus b square. Therefore, these two values are same. Therefore, may I say right sides of both the statements are same. Therefore, left sides will be equal. Means whenever we are having the two vectors x and y are linearly dependent, then modulus inner product xy is exactly equal to the norm x into norm y value. Therefore, Schwarz inequality holds if and only if x and y are linearly dependent. This may be a question for your objective. Na? Schwarz inequality will be equality if and only if dash 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 dash. There may be 4 options. Right? Okay. Therefore, here we end up with the Schwarz inequality. Okay. Now, we will go for the next theorem in which we are going to prove that inner product, square root inner product will act as a norm on the given vector space. Therefore, I will write the next theorem. No doubt by using a Scots inequality. Therefore, here we will write the statement: if x is an inner product space, I am writing shortcut, okay? Inner product space, then norm x is equal to inner product xx raised to half. That is root inner product xx is a norm on x. What we want to prove? Whatever is the relation we have obtained by between norm and inner product, that is norm x is under root inner product xx is also one kind of norm on a given space. I'll just add the pages. Yeah. Okay. Now we want to prove that this is a norm. Now if I want to prove that this is a norm, what one should do? One should verify all the 4 properties of the norm. Okay. Therefore, here we will see, here norm is defined as, this symbol is defined as, how it is defined? Norm xx is equal to inner product xx raised to half. Okay. That is, one can say norm square of x is equal to inner product xx. Who is the person wants an admission now? Jankar Usha. Okay. Norm square x is inner product xx. Now what we will do? We show that this norm satisfies satisfies the conditions of norm. The conditions of norm. How many conditions are there of norm? How many conditions are there of norm? Can anyone want to recall? How many conditions and which are they? Yes? How many conditions there are there of norm and which are they? One by one you have to tell me. Anyone can speak. Unmute yourself and speak. Yes? Whether someone want to speak or not? किती conditions आहेत नॉर्मच्या? Yes, 4 conditions. First condition?
Norm of x is greater or equal by 0.
Yes. Second?
Norm of x is equal to 0 if and only if x equal to 0.
Good. Third one?
Norm of x plus y is less equal by norm of x plus norm of y.
Yes, good. Fourth one?
Norm of alpha x is equal to mod of alpha into norm of x.
Good. Who is speaking?
Rohini ma'am.
Good. Okay. Now what we will do? We will prove all the 4 properties by taking this as a norm. Norm square x is inner product xx. Therefore, shall I start by proving the first property? To prove that norm x is greater or equal by 0. Okay. Now what is norm defined? Norm x is equal to inner product xx raised to half. Inner product xx is non-negative quantity, that we know, right now, because the first property of inner product tells us that inner product xx is non-negative. Therefore, this is a square root of a non-negative quantity. Actually, if I take a square root of a non-negative quantity, both values are possible, positive value and negative value. For example, if we are taking a square root of 4, what are the two values of square root of 4? Plus 2 and minus 2. Out of these two possibilities, we are taking the positive value here. Therefore, here one can say that this is non-negative. Both the values are possible. For the sake of proving this is a norm, we are taking the positive value. Rather, I will call as a non-negative value of the square root. Therefore, first condition holds. Let us go for proving the second condition. What to prove in the second condition? Norm x is equal to 0 if and only if x is equal to 0. Right? Let us prove. Okay, let us start. Norm x, or before that, by the definition of inner product, what the condition is there? Second condition of inner product xx is equal to 0 implies and implied by x is equal to 0. Right now, inner product xx is equal to 0 implies and implied by inner product x is equal to 0. Therefore, if I take a square root on the left, what will happen? This will be norm. Therefore, norm x is equal to 0 implies and implied by x is equal to 0. 0 is the value. Now, therefore, the second condition is also proved. Let me go for proving the third property, triangular inequality. Therefore, this is norm of x plus y is less than or equal to norm x plus norm of y. Okay. Therefore, let us start with the left hand side. Consider norm of x plus y. But norm of x plus y is square root inner product. Therefore, let me start with the square. Therefore, can I write this as inner product x plus y with x plus y. Okay. Let us use linearity and conjugate linearity simultaneously in first and second variable respectively. We will use first linearity in first variable. Therefore, this is x plus y added with inner product y with x plus y. Is anyone having a doubt how I am writing linearity in first and second variable? Linearity in first variable. Okay, first variable we have separated by using a linearity. Now we will use conjugate linearity in the second variable. But if I just look at the second variable, the scalars used here are 1 and 1. Alpha x plus beta y is the generally the combination, no? But here it is 1x into 1y. Therefore, by the remark we have seen after that characteristics, may I write this as simply inner product x with x plus inner product x with y. Similarly, inner product y with x plus inner product y with y. Reason here is conjugate linearity. Though we are writing conjugate linearity, scalars are real numbers, therefore no need to take the conjugates. Conjugate linearity in second variable. Okay, then what we have obtained the values. This first is norm square of x. Middle two terms is, I will just write inner product xy. This term I will write conjugate of inner product xy plus norm square of y. Okay, now what is the middle term? Is of the type z plus z bar, and we know z plus z bar is 2 times real part of the corresponding value. Therefore, shall I write norm square? This is 2 times real part of inner product xy. Is there any difficulty with this? I will just explain here. If z I am writing x plus iy, z bar will be x minus iy. What about z plus z bar? Then iy will get cancelled. This is 2x. But what is x? X is real part of z. Therefore, this is 2 times real part of z. Right? Same quantity we are using here. Inner product xy plus conjugate of inner product xy is 2 times real part of xy. Right? Now next step I want to use here. This 2x is always less than or equals to mod 2 times mod z. Right? 2 times mod z. Why? Because mod z is inner product, square root x square plus y square, and to the left we have 2x only. Therefore, depending upon y 0 or non-zero, this quantity will be greater than 2x. Therefore, here we can use 2 times real part of inner product xy is less equal by 2 times modulus of the quantity plus norm square of x. This is the reason. Z plus z bar is less than or equals to 2 times mod of z. To the left we have started this with norm square of x plus y. Okay. Now if you observe the middle quantity is modulus of inner product xy. But just now we have proved Scots inequality. With the Scots inequality, may I write this is less equal by norm x into norm of y plus norm square of y as it is. Okay, and the reason for this step is by using Scots inequality. Now look at the right part. Right part is now a perfect square of norm x plus norm y. Right now, norm x plus norm y bracket square. To the left we have norm square of x plus y. Therefore, taking square root on both the sides, we got this as norm square of x plus y is less equal by norm x plus norm of y. Hence, it is a proof of triangular inequality. Therefore, the third condition of norm is also satisfied. Let us go to the fourth condition. In the fourth condition, we want to prove that norm of alpha x is equals to mod alpha into norm of x. Okay, let us start for any scalar alpha. Na? Here we will write for any scalar alpha in C. Okay, therefore let me start with norm square of alpha x. According to the definition, this is inner product alpha x with alpha x. Okay, Now let us use linearity in first variable. Scalar alpha is taken out as it is. Therefore we remain with x and alpha x. Linearity in first variable. Okay. Now it's a time to use this conjugate linearity in the second variable. Now this scalar is taken out with a conjugate. Therefore we left with inner product xx. Reason conjugate linearity in second variable. Right? Conjugate linearity in second variable. Now alpha into alpha bar is mod alpha square into inner product xx. Okay. Now what is inner product x square xx? This is norm square of x. Therefore we have obtained norm square of alpha x is mod alpha square into norm square of x, which taking a square root one can write norm of alpha x is equal to mod alpha into norm of x. Hence all the four conditions are proved. Therefore one can say that this norm defines a norm on x. This norm defines a norm on x. Hence with the help of a relation between norm and inner product, we have proved that under root inner product xx is also one kind of norm. That is, this is also one kind of a distance measuring function. Okay. Any doubt till this? Yeah, any doubt till this? Okay. If there is no doubt, as you are not speaking, I will just assume that you don't have any doubt. Now we will just write an alternative definition of an Hilbert spaces. What we have studied a definition of an Hilbert space? Complete inner product space is a Hilbert space. Or I will write this as definition 1. Definition 1. What is the definition 1? A complete inner product space is called as Hilbert space. Okay. Now we are going to study an alternative definition. Okay. Let us just see what is the definition. I will just write the definition. A Hilbert space H is a complex Banach space. A complex Banach space whose norm satisfies or whose norm arises from an inner product whose norm arises from an inner product which is a complex function. Complex function means complex valued function. Complex function denoted by inner product x with y satisfying following axioms. Satisfying following axioms for any x, y in H. Let me write what are the axioms. First axiom is inner product alpha x plus beta y with z is alpha times inner product x with z plus beta times inner product y with z. Second, inner product xy conjugate is inner product y with x. Third, inner product xx is norm square of x. This is the alternative definition of the Hilbert spaces. If we just look at both the definitions, in the first definition we have started with an inner product. inner product space. Means here we know that all the properties of inner product are true, and then completeness was observed. In the second definition, it was started with a complex Banach space. Complex Banach space means the underlined field is complex field, and Banach space means it is the complete space whose norm is arises with an inner product. Means the norm defined on this Banach space is given with the help of inner product. How it was given? Just now we have seen norm x is under root inner product x with x, and is going to satisfy this following condition. If you look at the conditions, first condition is linearity in first variable, that we have taken already in the definition of an inner product space. Second is conjugate of an inner product xy is inner product y with x. This condition is also included in the definition of an inner product. Third is relation between norm and inner product. Once this relation holds, all the conditions which are true for norm are going to hold for inner product. That is, inner product is greater or equal by 0, inner product is 0 if and only if x is equal to 0, and so on. Therefore, second definition is very similar to the first one. The only difference is, it was in the first definition we are starting with an inner product space, then completeness was added. In the second definition we are starting with a complete space, where which is a complete Banach space I will call, which is a Banach space. That is, it is a complete space. Then a Banach space whose norm is defined with the help of a inner product. Therefore, both the definition goes parallelly. Therefore, one can say that every Hilbert space is a special type of a Banach space, but converse need not be true. I will just write here a remark. Every Hilbert space, is a special type of Banach space. Why special type of Banach space? The second definition itself tells us now, Hilbert space is a complex Banach space, right? But converse need not be true. Converse need not be true. That is, if I want to show you with the help of a Venn diagram, then this be the Hilbert spaces, and this will be a Banach. That is, Banach space category was bigger than the Hilbert space category, because every Hilbert is Banach, but Banach need not be Hilbert always. Banach need not be Hilbert space always. Okay. Now let us go to one more theorem in which we are going to say that inner product is jointly continuous. Let us write the statement. The inner product in a Hilbert space is jointly continuous. Jointly continuous, that is if xn tends to x, yn tends to y, then inner product xn yn tends to inner product x with y as n tends to infinity. Okay. Let us prove. What is the assumption? Xn tends to x, yn tends to y. Here assume xn tends to x, yn tends to y as n tends to infinity. Now our aim is to prove that inner product x and yn tends to inner product xy. We will just prove this by proving modulus between the subtraction of these two is tending to 0. That is, in real analysis we are using this concept. No? If I just want to show that if xn or if any alpha n tends to alpha, this will be equivalent to show modulus alpha n minus alpha tends to 0 or less than epsilon. Any one can use. Therefore, here we will start with modulus inner product xn with yn minus inner product x with y. And what is the aim? The aim will be to prove either this is tending to 0 or less than epsilon, whichever is convenient to us. Okay. In order to prove the required result, we will make an adjustment here. We will add and subtract a term inner product x and y. Subtracted, and we will add the same inner product xn with y. Okay. This middle term we have subtracted and added. It's a pure adjustment we have made. Now just look at the first two terms of an inner product. Here we can use the linearity in first variable concept. Therefore, I can write this 2 as one inner product xn yn minus y. Okay. And for the second, y is the same, that is second variable we will keep as it is. Here we will write xn minus x. Any doubt with this? Or if you want to go check reverse, if this inner product we have and I want to use linearity, then this can be written as inner product xn with yn subtracted with inner product xn with y. Okay. Now, this is modulus of an addition, which we can write less equal by addition of their modulus. So this is modulus xn yn minus y added with modulus inner product xn minus x with y. Now again we will use Scots inequality to write this is norm xn into norm yn minus y added with norm xn minus x into norm of y. Which inequality? Scots. Scots is helping us much while proving many of the results. Therefore, this is by Scots inequality. But what we know, xn is tending to x, yn is tending to y. Then what about norm values xn minus x and yn minus y? No doubt they are tending to 0. Therefore, here shall I write as xn tends to x, which implies norm of xn minus x tends to 0 as n tends to infinity. Similarly, as yn tends to y, norm of yn minus y will tends to 0 as n tends to infinity. Okay. Therefore, this term tends to 0, this term tends to 0, multiplied by a fixed scalar will tends to 0. This is also multiplied by a fixed scalar. Therefore, it will be tends to 0. Addition of two zeros will be 0. Therefore, in all, the left hand side which we have started with modulus inner product xn yn minus inner product xy will tends to 0 as n tends to infinity, which equivalently means inner product xn yn will tends to inner product xy as n tends to infinity, which proves that in the Hilbert spaces inner product is jointly continuous. Any doubt for the today's lecture? Yes? Is anyone having a doubt? You can ask now. 3 concepts we have seen today. Schwarz inequality. Okay. What is the second? Norm is a inner product. Third, we have seen just now that inner product is jointly continuous. If anyone is having a doubt on this, you can please ask me. Otherwise, we will stop because I think at 1:30 you have a second lecture. No doubt? Then we will stop for today. Thank you for watching.